Hey everybody, welcome to the stream. Another Sunday. We're going to do Essentials of Compilation today, as advertised. Hopefully that window's not too bright behind you. And let me know if there's any technical difficulties. I'm running a little bit late and I had to rush to the stream, so here we are. So last time we got remove complex operands done. And if you remember, that was about taking any expressions that cannot be that cannot operate over things that are nested expressions. So you can think of like our primitives or calling functions, which is our new thing in this chapter. Their arguments to those operations, is the best way to put it, have to be atomic. So they have to be variables or constants, basically. And so we did our transformation. It removed nested complex expressions from our intermediate representation. And today we're going to take the next step, which is sufficiently more complicated than what we did for that. And it's going to be turning our function expression-like language into something that's a bit more imperative. They call it three address form, but in the book they've been using this, they've been calling it C-like language. And why they say it's a C-like language is that you basically have very few kinds of constructs. You have a sequence of statements, so to speak, and those statements are usually assigned to a variable the result of something else. But you can also have jumps for our conditionals, and we'll be introducing calls for both the inline calls as well as tail calls. So we're going to get into that today. Let us have a look at where we are and get started. Hope you all are excited about this, because I am too. All right, so realize that's underneath my face. Okay, so we're looking at, and I'm going to hide the sidebar so we can get a little bit bigger. We're looking at explicate control. So explicate, very, very funky word for this. But basically what it means in this context is that we're making control explicit rather than implicit by the associativity or the nesting of expressions, right? So we're going to turn it into away from this expression has these expressions nested into it, and turn it into this is a sequence of things that we're going to do to accomplish the same task. So we're actually changing the semantics here in this IR. I say we're changing the semantics. We're changing the way those semantics are accomplished. Hello, welcome to the stream. All right. Okay, so we're gonna do that. Let's have a look at our code, and I'm gonna have to restart Zed one more time. One thing I appreciate about Zed is that they are constantly updating it. But also means I have to restart it every single time I have a stream. So, okay. Let me make sure I did push. Okay, so this is a cool new feature. Zed, we finally have Git history. So last time, we did chapter 7.6. We made this Elmon funref language. I say language, it's an intermediate representation. And then we updated remove complex operands to support that language as opposed to the one that it previously supported. Okay, cool stuff. So today, let us get going on this. So I'm going to pull up the standard lib. There we go. We can have that ready. If you want to follow along with the code as we go, remember you can always go to this GitHub repository. In fact, I'll paste it in the chat for you all who are new, if it'll let me paste. Paste. God, that was harder than it should have been. Okay. So this is where we're doing everything, and I try to push at the end of every week. If I don't, I'm very sorry. And let's get going. Okay. So clear out some of the things that aren't needed here. All right. So our first step, I think, is going to be updating the syntax of this intermediate representation. So if we look in here, we have various versions of this C-like language from previous chapters. So we have one with variables, we have one with ifs, we have loops, and we have tuples. And those were the last 4 chapters, basically. CVAR maybe came before, because I think that I want to say chapter 3 was register allocation, and that was its own journey. Okay, so we're going to make a new one, and it should be based on what we did in the last chapter, which was C-tup. So let's read for a moment, and then we'll get going. Okay, so 7.8, which is down below, defines the abstract syntax for C-fun, the output of explicate control. The auxiliary functions for assignment and tail context. So if you aren't here for the previous ones, we call transformations based on what position the expression is in. So assignment is the right-hand side of a let expression, basically. Tail is this is what would be returned from the program, right? Or from the function in our case. So we're going to have to apply that to functions as well. Okay. They should be updated with cases for apply, which is the operation we introduced in this chapter, and funref, which is a pointer to a function, basically. And the function for predicate context, so basically the conditional in an if or a while loop. Function for predicate context should be updated for apply, but not for funref, and that makes sense because funref cannot be a Boolean. So what are we going to do here? We're probably going to panic on that branch. And apply is, basically calling the function. Okay. So here's the abstract syntax. This is, okay, that's x86. So we're going to add funref as an expression. That makes sense. We're going to have call as an expression. We're going to add, and so expressions can be inside other things. Tails can only be at the top level. So we're going to have tail call. This is where we get tail call optimization for free. I put that in air quotes because it's not exactly free. It's just that we did the analysis and we know this is in tail position. So we can jump. Okay, and then we're going to have definitions. So definitions are new, and it's basically that instead of being a function, we'll have the list of arguments still with their types. We'll have the return type. They use this info thing arbitrarily. We don't have it yet. I'm only going to add it if we need it. And then we have a set of blocks, which are a label and a tail. I say set of blocks, we'll use a dictionary. And then the whole program is a set of definitions, one of which happens to be main, right? And we did that previously in our other intermediate representations, where we turned a program which is a set of definitions and then one expression into just a set of definitions where one of them happens to be main that has no arguments and returns int, right? Okay. So let's get going on that. So I'm going to duplicate C-tuple, and we're going to call it C-fun. C-fun, have fun. Okay, so we have a new expression type. And let me get this split to the left so we can just do that. Nope, let's just hide everything. Okay, so expression, we're going to add funref. And this is going to, are you trying to make a compiler? Yes, yes. Sorry if you're new to the stream. We are using this book called Essentials of Compilation. So I linked to it up here in this repository. It is a compiler course for Indiana University, and the book and the support code are all public. None of the actual implementation is public, so you won't get that. But that's like the point. It's didactic, right? The goal here is give you enough so that you don't have to write the things like a garbage collector, right? And get you focused on what the compiler does. So go look at that. You can download, you can build it yourself if you have the tech toolchain, LaTeX, or you can just download a version of the PDF from releases, which is what I did here. So go check that out. All right. So a fun ref has a label, and I think I want to be consistent with what we did before. Wrong one. So let's look at Elmon fun ref. Okay, what did we do before for fun ref? Just name and arity. Yeah. So let's just copy that because I think that's going to make it easier. Okay. And expression can also, let's move it down to the bottom. Expression can also be call. So over here we call it apply, but we're going to use call, which is going to be basically this. Okay. And I think the reason this is called call instead of apply is to get it closer to the ideas of a like what it's actually called in the x86 assembly. It's call queue, right? So we're saying call a function, and those are the set of arguments. Okay, so tail, so what can be in tail position? You know, I mentioned it's just like what's the return value of the program. Not exactly. In some cases, because a tail could be a block where the block is not, it's part of a larger sequence including conditionals or loops or so forth. It will maybe not be just a return, so or a sequence. So we could have, you know, a goto is a fairly typical thing in the blocks that are generated from implementing a loop, for example. So or for ifs, we actually break the true and false into tails, into different blocks sometimes, and those become gotos. So that's another possibility. So we're going to add tail call to this. And I think it's going to look like call, but it's just going to be tail call, and then it's have to be atomics. This is the AST part, yes. So you can think of this as a middle portion of the compiler, and the strategy of this. So we are building ASTs. These are the ASTs of an intermediate representation. The strategy of this book is lots of little phases, which most of them produce a new intermediate representation. And then what you get out the end is is basically x86 assembly that you can build with an assembler. So we are doing all the stuff in the middle. Okay, and so a program here, we need to update that. It is no longer, we'll have the info. I don't know that we will use it, but the body, we're actually going to have, we needed to make a definition. So IR plus AST. Well, so intermediate representation is just another kind of AST. If you look at the original AST that we produced at the beginning, so let's see, where's L-Fun? I mean, it has a lot of the same structures or similar structures. This is an AST, right? Um, but at this point, you could say that this is an intermediate representation. It just has to be the first one, above the lexical structure, right? You could say the list of tokens that are produced from tokenizing is an intermediate representation. It kind of is. So anyway, yeah, the distinction there is murky. Okay, so we need to change this from the body just being a list of blocks or a dictionary of blocks. We're going to have to make a definition. And this is going to look like what we did previously. So I'm going to call it definition. And it's going to be, they're saying label. We're going to have to import elfun types. Okay. So label. What do we call? I know they say label here, but I think that we called it name. We called it name. But name arguments return body. I just want to make this as consistent as possible rather than changing it arbitrarily. Arguments is a list of strings, variable name, and type. Right? We imported type, so we don't need to qualify that. Let me hide this sidebar again. Return value is a type, and then I guess we'll call this blocks or body because that's what it was called in the original. Okay, so we'll say body. This is going to be a list of blocks, and now we're going to say, rather than body, this is going to be defs, which is going to be a list of definition. Okay, so now we're going to have to fix the pretty printer because this is useful for understanding what we're producing at each stage and making sure that it looks okay. So we're going to make this pretty printer do its stuff. Okay, so I think we're going to have to do, let's make a function which is format definition. The interesting thing here is I don't know what that should look like. Maybe we put a comment in there that says this is this definition, because when we get to the point of these being blocks, they have to be uniquely named across all definitions because that's a label in the assembly, right? And they don't have a concrete syntax of cfun here. Well, let's just go, let's damn the torpedoes. Full speed ahead. Okay, so we're going to take we kind of want to do what we did here, right? Let's start with that. Let's just say def.body, and we will add to it as we go. To list map, and we're just going to copy this because it's the same thing. Doc concat. Okay, and then here, I think we need to do. I commented out the force break previously. I'm not sure if that's necessary. We need to put something in here that mentions that this is the name of this function and its arguments, maybe we can use something from the L-fun language to format the arguments and the return type. Format. We can do format type. What do you think about this? Because I want to show it's going to be like a comment, right? The question in my mind is, what are let's say ASM syntax, x86 ASM syntax for comments. Let's just Google it real quick. Semicolon. Okay, that's kind of what I expected. Yep. So we'll just do that. Okay. That's not a problem. Okay, so what we can do is say let's look at what format block does. Okay, so it puts the label for the block and then a new line with the colon. Okay. So let's do. We don't need to nest, but we should preprint, I think. Or maybe we just make them a sequence. All right. Let's make a header thing, which is just a document, concats, and we're going to say doc from string, and this is going to be semicolon space, right? So that we get the comment. Maybe we could do 2 semicolons, and then let's say def.name. Doc join. Yeah, let's switch this up with concat join. Concat join with doc.space. Okay, and then we need to put the arguments in there. The thing is, these become local variables, right? The arguments do. And we'll say let body is this, and then we're going to say doc concat header body, and then we'll be happy. So let's fill out the rest of this. Doc concat join list map over def.arguments. And that's going to be a function that takes cat. Sorry if this is getting messy. Let's actually, before we go too much deeper, I want to jump to what we did up here, because we have the formatting of arguments. Format argument. Let's just make that pub. And then that'll be easier. Yeah, so this has defines and so forth. and then I don't have to reproduce that. Okay. I need to hide that because I'm running out of space here. We don't actually need this for now, so let me get this to full, and then we don't have to worry about that project sidebar. Okay, so let's do format argument. Yeah, and let's just use the import there. With doc.space. Okay. And we'll have from string. Remember that a return type has a colon before it. Let's see, l.format type def.return. Okay, and that should be enough to put in the header so that we can see what that function is. Now the blocks are going to be named after, like they're going to use the name definition as a prefix, at least I hope. And then, yeah, and then we can do format block and just combine those, and that'll be our definition. So now we can get rid of this, and we can say concat list map over input.defs of format definition. So that's a much more concise way to do that. Okay. And then we have the comments there for posterity so we can see what the heck is going on there. Okay, so I think, what's wrong here? So now we have some new constructs in our language. Let me hide the shell. So we need to handle each of these format things. So tail call. How are we going to do that? I think that we'll say if we look at what they say here. Now I want to look at how we're formatting other things. Okay, so it kind of looks like C-ish. Go to if else, so forth, return. So I think I want to do let's just say it's call, or maybe we'll say tail call, like that. I think that that's not a thing in C. Doc.space. Let's just say concat. I don't know that I want to join this. I might want to join things on the inside. Okay, doc from string tail call. And then let's put a space. And then let's use format ATM, format atom, a function. And then we're going to put let's put an open paren there to signify the arguments, and a close paren at the end. Form string from string. Okay, so now we can do list map format. We're going to do doc concat join with, and we're going to say from string comma space. Okay. So we're going to map over arguments with format ATM. Okay, so we can just format Atom. Okay, so we've got tail updated because the only thing added to tail, the tail type, was tail call. Okay. Now statement, we didn't add anything. ATM, we should have added something. No, we didn't add an atomic. So it's expression where we need to update, add missing patterns. Okay. So I think that what we'll do here is something similar to what we did for tail call. So I'm going to copy pasta some of that. Remember when we did the actually let's put a semicolon after that because return has a semicolon. If has indentation. Okay. Is the compiler for C language syntax? No. The compiler is for a racket-like Lisp language. So, you know, have a look. I'll scroll up to the beginning of this chapter so you can see what we're doing. Whoa, too far. So... well, here's an example. So you can see, you know, there's let expressions. This is a thing with while loops and tuples, so make vector. Tuples are basically structs, so fixed length collections, heterogeneous collections. And, you know, the implementation in here is in Racket. So it's a Racket-like language implemented in Racket. But we are taking the Racket-like language and implementing it in Gleam. So not exactly the same thing. But let me just use the table of contents and jump back to where we were. Okay. So we'll do something eventually when we get through as much of this book as I want to do. We'll do something else compiler shaped, which should be fun. I have some ideas on that. Last time, Willie, who comes to stream multiple times, he talked about maybe you could do the implementing a C language in Gleam. That could be fun, but I haven't decided yet. Okay, so let me take this. We're going to copy that because we're going to use that for call, except that we are going to do. We're going to not put the semicolon, and we're not going to say this is a tail call. This is just a regular call. Okay, but we can use that same format. Okay, for funref, we're going to do like what we did previously, which is going to be, we're going to concat the name and I'm sorry, this is like not really fun code, but it is necessary code. Arity. Okay, so what I'm doing here is I'm saying this is the function that we're going to call. It's going to have slash as the arity separator. It's a very Erlang-ish thing, and then we're going to put the arity in there. Willie is always here. Hi, Willie. Thanks for coming. Okay, and then our last bit, I don't think we're using this main, so I'm going to just delete it. Yeah, we're not using that main. Okay, and then we don't need Gleam IO. I think I was trying to get to a point where we could, use this without having to have so much of the web-based interface implemented, but Yeah. Okay, so now we have all this defined, and it can be formatted for the yeah, it can be formatted for our web page. Okay, so let's have a look at actually explicate control, and this is where things are going to break, and it's going to be kind of a pain. So now we need to say we need to update these. So we're going to update this as cfun. Elmon alloc is going to be elmon funref. That's going to be our input IR. And ltoop is our original. It's lfun. So that has the types and so forth in it. Okay. So right. Okay, so we're going to say this is note that input body is not there. So we need to do basically let's see what they say. Right, so we can look at the auxiliary functions later, but I think that the interesting thing is we recommend defining a new auxiliary function for processing function definitions. This code is similar to the case for program in L2, right? The top-level explicate control function that handles the program defs form of lfun can then apply this new function to all the function definitions. So this is really, we need like, it doesn't need to be pub, it can be fun explicate definition. And then we'll take lmon.definition. And this is going to return C definition, right? And most of this stuff is going to move down. And then what we'll do here is this will be C definition. And then I think that we need to do something other than start. I think this actually needs to be def.name, right? Because that's what will be jumped to. Okay, so this is body. Is that? And we need to go. Name is def.name. These are just straight copies over because we have return def.return because we have the same structure there. Okay, so we'll say def body. And right. So this explicate tail just needs to change for the new types of tail position expressions we have, like anything new that's in our input language. And then what we can do here is we can say input defs list map explicate definition, and then C program dict new and construct it. I could inline those for what it's worth, but yeah. Okay, so this isn't so bad. except that we have to deal with all our new types. So this got renamed to condition, and let's put that here. Okay. And is this just complaining about missing? Add missing patterns. Yes, let's move these up. This is explicate tail. Okay, so let's see what they say. It's not wrong for a function to return a function, by the way. So funref is okay in tail position. Okay, so we'll worry about predicate contexts later. Assignment and tail contexts, those can receive apply and funref. The main difference here is that for to do, what we want to return is C funref name arity and blocks. That doesn't introduce any new blocks, right? And since name, oh, it needs to be a tail. So this would have to be C return of funref. Does that make sense? So this is like, we're talking higher order functions here. So we can return a function ref from this position. Okay, so the apply though is going to be tail call, right? Function, and then we need to say how did we convert? Is there a convert ATM thing? Explicate convert ATM. Yeah, so let's just do convert ATM on all that. Convert. Yeah, I should have just tried it. And we'll do list map arguments convert ATM. So here we're not adding any new blocks. Apply does a tail call on that function. Okay, so tail position was pretty easy. Let's look at assignment position. And this I need to rename. I didn't do that right. It's actually conditioned there. Okay, so we need to go down here and let's add the missing patterns. So assignment, right. Okay. It's going to be similar to these other things that we've looked at before. So this is going to be, and remember this, in assignment position, we're using continuation passing style. So we need to make a sequence which has a sign. And the string is V, right? And here we're going to have C funref name arity. And then sequence takes an expression. Let's see if I can get the, I think that's right. Number of params looks right. Okay, blocks. This doesn't create a new block. Okay, and then we'll do something similar for this. Except this is going to be c.call, right? And then we need to do that convert ATM thing that we did above. So we'll just grab this. Note the difference there between call and tail call. They're not the same. Okay, so we assign to the input variable, or to the variable on the left-hand side, the result of call this function with these arguments. Okay, that one wasn't so hard. Let's look at explicate predicate. Now here, again, we renamed this to condition. I don't know why. Okay, so all of these other possibilities we have not handled. So I think that what we do here is let's add the funref can follow through, but we need to do apply in predicate position. Excuse me. Okay. So that is a potential danger here, that we ignore some things. But if you look at what's down here, none of these things can return Boolean types. So, because while returns void, this returns void, this vector set. Vector length returns an integer. Read returns an integer. Plus returns an integer. Negative, all those return ints. Set bang returns void. Collect and allocate returns a pointer internally. It's an internal GC thing. Global value looks up a global reference. So those are not valid in predicate position. Funref is also not valid in predicate position. So I'm going to go ahead and put in a case down here just to show that we are covering it. Funref name arity, because that's a function reference is not a Boolean, so it cannot be the value of a conditional. Okay, so for apply, I don't think we need to create any blocks, because as long as we've type checked that the function being called returns a Boolean, there's no reason for this not to just be call. Let's look at var. It'll be kind of like this. Okay, so what we need to do is we need to generate the if. Interesting. So it kind of needs to be like this. I think sorry folks, this is complicated code because we are actually changing the behavior, and continuation's passing style always messes me up. Okay, so let's look up at explicate assign, because that's going to tell us what we need to know. If we're looking at if, so we say right, so we create blocks for the continuation. check what comes after the if. Okay, and then we treat the if true as an assignment to the variable, right? Because if we're in assignment position, the result of this if expression is going to be assigned to the variable, right? So we're doing explicate assign here. Maybe we can look at explicate tail as well, just to see what happens. Okay, so we create a block which gets called essentially for the if true. We create a block that's called for the if false. And then they both branch to this whatever comes after, right? They don't branch. It's like a diamond shape. You go this way or that way, and then you come back to the same conclusion. And then we call explicate predicate with whatever the expression is in the condition. And that doesn't have to be atomic, right? And then we have true, false, and then the blocks, the set of blocks we've created. Okay, so let's look real quick at explicate tail as well, what it does on ifs, because I want to understand that. And then we will have... Okay, so if, yeah, just does explicate tail for each of these, and then calls explicate predicate, because these are both tails, right? And you don't jump back, because this is in tail position, you don't go back to something else that happens next. There's no continuation in tail position. Okay, so basically whenever we call explicate predicate, we're calling it from the position of, I need to reconstruct this if. And you'll see here we do some self-recursion. If this is a not, then we swap the if false and if true blocks. If there's a let in okay, so this is saying yeah, so it's like, hey, we need to treat this expression as a predicate. And then we do an assignment, wrapping that. Okay, what are these? Okay, so this is an if. This is inside. So this is an if inside an if. So if the if is in the condition position, then we have to call explicate predicate on both both branches, right? Because those are both in predicate position, and we call it on the outer, right? And then begin is all about it's like this result expression is the conditional, and so you take it and then you wrap it with effects. Because the value of those intermediate expressions in statements here is thrown away. So you only execute them for their side effects. That's why it calls explicate effect. Okay. So I think that... Where are we? So an explicate predicate, it feels a bit like these. That what we will do is we'll create a block right? So let's do that. So let's create a block for each of those. And then we just return an if with the new blocks. I think that feels right. So if can take an expression, and here's where we want to put our call. This is call, right? We do convert ATM again, function, list map, arguments, convert ATM. Then block, else block, and we return B2. Yeah, I think that's what we do. Because there's really nothing more to be done here except to like reconstruct the if. This is pretty small. There's nothing nested inside those where they're already atomics. So unlike begin, which is, you know, a bunch of expressions, or you know, this is a nested if, so you have to go into the condition here. Okay. Let's see. Function for predicate, but not for funref. Okay. In assignment and predicate context, apply becomes call, right? That's what we did. Whereas in tail position, apply becomes tail call. Okay, we did the function definitions. This code looks similar to program for del tube. Top level explicate control function handles. Okay. Is there anything else in this section? No. So I think that what we need to do now is make sure that we get it covered in every place. So in effect position, we need to handle funref and apply. I would say that what we should do is not omit anything. But we can't do that. So funref obviously has no result because it's just a reference to the function. It's just the name of the function. We're not calling it. Apply, because the arguments might be, they're not guaranteed to be immutable, right? They might be a vector. You could pass a vector and then call vector set inside that function as a side effect. So I think that what we need to do here is okay, so funref, I think that we just return continuation and blocks. And I'm going to put a note here, has no side effects. Apply, though, what can we do in effect position? We need to return a tail. So I think that what we do is we make a sequence. And then a sequence contains another tail and the continuation, and then return blocks. I think we need to have an assign here, and I don't. We need to create a fresh variable. What do we do on these other things? Yeah, we use assign for, okay, for set bang. Okay, for read, we have a read statement. Maybe what we need to add here is a call statement. The thing is that feels like tail call, but we don't want it to be tail call because that is just a jump. You never return from tail call. If you have any thoughts, throw them in the chat. I feel like what I should be doing is assigning this to. So what does assign take? It takes a string, so I'm going to assign it to that. But I kind of need to make sure that that's unique because it could be treated as something that we have to allocate to. And we didn't handle that in previous phases. Feels like there should should have been handled previously. But it's not a concern of a previous phase, really. Let me look at the book real quick, make sure there's nothing I missed. So at the end of every chapter, if you haven't seen this, or toward the end of every chapter, they have this graph of like what the phases look like. You know, it's basically a list, but they're showing the intermediate representations along the way. And we're here, and we didn't do anything that would handle a call, like an apply, in an effect position. So inside begin. We have this create label, but that is only for blocks. Well, let's go forward with this, and I'm not going to like it, but we will do it. So call. And here we are doing that same thing again. It's fine. Repetition is fine. Okay, so here we don't care what those are. We could probably put funref up here. Yeah, let's just put it with the rest of these that don't modify the blocks. We can get rid of that. Okay, I'm not feeling great about this. We could use create label and just give it a prefix that's like yeah, let's do that. It's not right, but it should. We'll call it apply and then blocks. What it will mean is that if we have multiple calls for the sake of their side effects in a begin, they'll all get assigned to the same. The result will all get assigned to the same variable called apply, underscore whatever. And I think that's okay. And maybe I can put a leading underscore on it, just to emphasize that it's thrown away. I think that's an acceptable solution. I'm not real happy with it, but we need to be able to move forward. So I guess the remaining questions are, what do we do here? Okay. What are we missing? The other thing that we might want to do is wherever we're creating blocks, we should use the definition name as a prefix. So I want to make sure that we don't have collisions, because each of these definitions is going to have their own set of blocks, right? So I think that we need to throw another argument in here, which is def.name as the prefix. And then the other option is we put it in this type, this blocks type, like reify that. That might not be the worst idea. And that's just a type alias, right? So yeah, it comes out as a dictionary. So if we did blocks, if we make it blocks is this, and the prefix is a string, then we don't really need to change those things. We just need to look at the prefix when we're generating names. So let's just do that. I think that's the only thing we need to change in here. And then over here, what we will do is let's let me pass blocks here. And then we're going to have to update that's going to be horribly confusing. I'm sorry, but there we go. I'm just going to do a struct update there. And we can probably do let body equals that, and then it's a bit more clear. Okay, so now every place, I don't have to add a new argument to these functions. I just need to update the places where we receive blocks. And then maybe I make a helper function. Let's say insert block, which is going to take blocks, and then def.name and tail, and it's basically gonna look like dict insert, but it'll update this thing. This is really just so we can thread this through. No, here, what do we do? We're gonna generate definition, generate function. I'm gonna put it at the end. And it's gonna go up in here, right? So we're gonna have to go looking for places where we do dict insert and go insert block, like so. All right, and this is just going to be blocks. Are you confused yet? Blocks.blocks, name, tail. Okay, so that's not a big deal, but just too many things with the same name. Okay, so for create label, we'll just update that. Here, I think that what we need to do is say blocks.prefix. Okay. And then those will be ensured to be unique. So now, interestingly, this, what we did up here, okay, this needs to be insert block. This create label is going to have the prefix on it, is it not? No, it won't. I guess that's okay. It's local. We really only need to do register allocation on local variables independently of one another, independently of different definitions, right? So we don't have to care about what some other definition does because it has the ABI contract about what registers are used for calling conventions and so forth. So yeah, this is fine. This is going to create duplicates, but that's okay. They're going to be different control flow graphs. Okay, so I think that's pretty good. That'll ensure that those blocks are uniquely named across the entire program. You know, the numbering of them has to do with the internal numbering for each definition, but we name them with whatever the prefix is, and that's fine. Then you won't have any jumps from the middle of one function into the middle of another one. That would be bad. Okay, let's see what's wrong here. Okay, so we need to find the other places. Insert block. Up here, another one of those. Insert block. Where else do we have bugs? I think that's it. Okay, that's the only place in this file where we do dictionary inserts, so that's good. That's good. Okay, so now I think the next step before we go on, and hopefully we can do select instructions. I know Willie was excited about that. Wanting to cover double. So let's get the tests working for explicate control. You know, as we do with all of these, we commented them out because they just don't work. And I need to update the helpers and so forth. So let's start with, this needs to be C fun. This needs to be C mon fun ref as lmon. This needs to be L fun. Okay, and then we're gonna have problems here because, yeah, the program's all wrong. Let's go down to the bottom and fix this to be more like what we did in previous phases. Like, let's look at uncover get test. Yeah, we can do this. Okay, so we're gonna okay, so we need to import type check program, reveal functions, import that, limit functions, import that. Okay. So the big problem with updating these tests is a lot of the assumptions that we had in previous passes are going to be broken. So let's consider each one of them individually. Obviously, this file is not going to compile yet, so we can't even run the tests. But what we need to do here, and we've done this transformation before, this is a list of definitions. So we need to do lmon.definition. And this is main, and it has no arguments, and it returns integer t. And then this is the body. Okay. I think the difference here is this is fine, but this is going to be main, not start. And what we want is blocks that, and main is the prefix. Okay, but that's not entirely true. So we need C definition as well. And again, it's going to have no arguments, integer t, and this is going to be a list. Okay. So, you know, main is still special. But what we could do for now is comment out these other tests. Don't worry about that warning. And then see if this one works. Okay, so that one passed. So our semantics are still the same for very simple programs. That's good. All right, let's break down the next one. And we're going to do this transformation of our test cases multiple times. The difference being, well, we're going to start to see some of the new things pop in here. Okay, so save that. This should not compile. Oh, I'm missing some stuff. That's why it's not compiling. Okay. All right, so let's see if we can copy some of this stuff and reproduce it more easily. We need another one of those. Okay, so that's up to date. And this needs the C definition, so very similar to what we did before. The difference is here, oops. So this is going to need to see blocks. And main. All these blocks are going to get renamed, though, is the part of the problem. Okay, I got too many commas there. And all right, let's see what we got wrong. We need another one there. Okay. So these are going to be, this is actually going to be called main, not start. Remember, we changed that. This is going to mean we're going to have to prefix each of these. It might be interesting to see the, let's just put back to start, see what fails though. So let's just run Gleam test. Yeah, so we got definition main, that's all fine. This is main. This is, we expected block 1, block 2. This is main block 3, main block, you know, all that stuff. I suppose that we could remove that block prefix from there and just say main underscore 2, main underscore, and so forth. I think maybe putting it in is good though, in case somebody calls their function block. This is why compilers have often have really complicated name mangling schemes to make sure that they're unique. We're not that cool. Okay, so this is main, and then for all these places where we have block, we're gonna prefix it with main block. And I'm just gonna paste, right, because what we're concerned with here is not, we don't really care about the names, we care about the control flow. So let's see if that fixes the test. It should, yep. All right, let's re-enable another one. Okay, so again, wish there were an easier way to do this wrapping. Put parens around it like that. Okay. Main empty list integer t. Okay. And then we can do that's the spot we want to put that in. Okay. And I think that I kind of want to just do some of this. Cut down on time needed. Okay, that came out correct. I need to update this. Okay. Let's run that test. Okay, so now we're actually getting, I didn't rename this. This needs to be main. And this one up here, main. Okay. Cool. This test is kind of interesting. So eliminate constant conditions. Basically, if you have something that's like a constant Boolean, then there's no reason to put the other branch in, so we just eliminate it. So if true, 1 or 2 should just be return 1. And similarly, if not false, because this is about turning not into a swap of the branches. So what you do is you say for this, not F. If it's F, then you would just return the else branch. But if you swap the branches, then it become the 1 becomes the else branch. So you should get return 1 as well again. Okay. Let's do the next test. And I wish there were a way to do this faster, but I'm on stream. We're going to get it done. We will live. It's not so bad. Now I'm going to have to include the blocks constructor. And these are all for simple things because we haven't gotten to actually calling functions in explicate control. We should look at that. I think that it'd be interesting to have some good tests there. Okay, so that's main. This is main block 1. Main block 2. Okay, let's make sure that test passes. Okay, no failures there. We're getting there, folks. We're getting there. A lot of these were written, you can see, where were these last touched? Okay, 2 weeks ago, but before that, because that was when I commented it out so we could start doing this chapter, I think. And again, I'm missing this. Oh, okay, so this one is a little bit weirder. I think that what I want to do instead of this is I want to do, let's just write it in let's write it as program text instead. So what are we doing here? So we have if and EQ read 0, and this is about sequencing, I think. EQ question read 1, then you have 0, 42. Right, so that's the original program. We can comment this out. Okay, So let's do our transformation we've been doing before. Replacing all this jazz. Let's shrink that so I can see it. Main. We need to close blocks, close definition, close list, close program. Oh, okay, so we need to do let's change this back to explicate control, and we're gonna put this say it's parsed, it basically that it's gone through all the other phases that we need it to go through. Okay, and this is gonna be wrong because this needs to be main and so forth. Okay, so what's going on here? We have an if, we're doing and on each of these conditions. Each of these conditions is checking, read an integer from the console input. Is it equal to 0? Read the next integer from the console input. Is it equal to 1? And there's a lot of stuff that happens to get there. So let's see if we get equality. Okay, yeah. That turned out right. So the way this has to do also with how it unrolls and is shrunk into an if statement or an if expression in that shrink phase. So we call this shrink. It turns ands and ors into ifs, and one of the branches will return true or false, and then the other one contains the nested expression. So yeah. So and would be like, if the first one is true, then return the second one, otherwise return false. And that's what it changes it into. So what we get here is an if inside an if. And that's what this test was testing. Let's see. I think, yep, we're starting to get better stuff here. All right, let's copy this business. I'm sorry, again, that this is not the most exciting content right now. Main. Okay, so blocks is closed, definition is closed, list, definition. Okay. And this is going to be main again. This doesn't have any jumps. So, okay, I think that yeah, this is just showing that begin turns into that. This is exercising explicate effect. So we do assign read to x, and then it assigns temporary variable 1 to x, and then we do the set x plus x1. Yep. Okay. Let's see if that one works. That passes. We're doing good. We're almost to the end. I'm sorry. That's a big one. 2 more tests, it looks like. Okay, this one's about loops. So this is the program. Why don't I like unpipe that? Yeah. So this is a typical sum the numbers from 0 to 5. Well, it's 5 down to 1, I guess. Yeah. Okay. Let's get this business again. And then I'm going to collapse that dictionary from list, and we'll say main. Block, then the definition, end of list, end of program. Okay. So now I need to update the labels here. Okay, so this is no longer, this has got to be main loop 1, I'm guessing. At least I hope that we're doing that. I guess we'll find out. And all these other go-tos get main prefixed on there. Main. We're going to have to look at how that gets created. Make sure that we're consistent. Okay, we got a failure. So there's a place that we need to update in here. I wish rich diffs were a thing, but I think that we can figure it out. Yeah, so it's just using loop. So we're going to have to go up here and let's look at while. Okay, so we need to do create label. This is the reason why this happens ahead of time, I think, is because we don't have the block yet. We just need a label for it. So you know, the other thing that we could do is put this, and this is probably the wiser thing to do. Just put it in there. We haven't tested any of that apply stuff yet, so we have the opportunity to change it. Let's see if that fixes the test. Yeah, so the fact that we carried that prefix of the definition name in there meant that we could, in this block struct, meant that we could do that pretty straightforwardly. So now they're not going to conflict, etc. We're good. Okay, let's go back to the test. One more, and then we'll add one for apply, and probably fun ref, and see what we get. We might want to do something like something simpler than all this business, but let me grab our boilerplate here. Shoot. Not exactly what I wanted to do. Let's go to the end here, and I think that we can figure it out. So we need to do comma main, close that, close that, close that, close that. Okay, so now we have a problem. 4 arguments got 5. 2 arguments got 1. Okay, so I have an associativity problem down here at the bottom. Okay, that fixed it. Loved having strongly typed languages for these problems. They save me a lot of time. Thank you, Gleam. Okay, so we need to put main at the as the prefix of all these blocks. Look for go-tos and block names and so forth. Copy that. The reason this this simple vector program has vector allocation program has blocks is you got to check the garbage collector to make sure that you have space to allocate that thing before you can allocate it. And so you essentially have test it, test if you've got free space. If you do, then you can continue. If you don't, then you have to jump somewhere else. You have to go garbage collect. Okay. Make the typed racket dialect to target beam. Yeah, so the reason I wanted, and for Willie, I'm really glad you're here lately. But over a year ago when I started this series, and I took a break last fall to do some like tiramisu game programming stuff. The reason I started this was years ago I tried to write some stuff in Elixir that directly targeted like beam assembly. In retrospect, like that could be a nice learning experience, but it's not particularly useful. Partly because beam instructions, they're not well documented. I guess they're enough if you're working on the compiler, the Erlang compiler, but both Elixir and Gleam target Erlang, right? They compile down to Erlang ASTs, which you could do with this with like a typed racket. There exists LFE; it's non-typed, but we could do the thing that the big things that would change is you could never have mutable variables. Like everything would be an expression returning a new value. But yeah, that's actually a very tractable thing. People have done it multiple times. Is write a Lisp for targeting the beam. There's LFE. There's JOXA. For a bit, there was a scheme that was being written by Joseph Wayne Norton for the beam. Could be a good thing to do. Anyway, let's run our test, and it passes. Okay. So before we go on, let's do, what is this going to be called? Explicate control something? Yeah. Explicate control call function test. And I want to make this large enough to be interesting, but small enough that we can actually figure out what it should look like. And I think that what we do is, let's say, define inc, and it's going to take x, integer, and it's going to return an integer, and we're going to do plus, this is a dumb program, right? But then let's do plus, or we're going to do inc 41, of course. The result has to be 42, right? Jox is dead project. Yeah, someone forked it. It was just for fun. Be typed list flavored language and a typed top. What do you mean by top language? You mean like Gleam? OOP language. Oh, okay. Yeah, I think OOP is a dead end. Rhea existed. It kind of showed that the paradigms are too different. I don't think that that's a useful thing. You might be able to get by with doing dynamic dispatch by putting function references into your type. But yeah, that feels a bit like a dead end. Yeah, I mean, like, please continue giving these ideas, but I disagree that OOP is something to try to emulate on the beam. I think what it too often sends people down is, oh, a process is an object and I'm sending it messages, and like that's not what processes are for. Yes, they can contain state that is isolated, but that's not what they're for. They're for resilience and coordination patterns and so forth. So if the folks who had invented Erlang had been able to accomplish their goal of resilient programs without processes, they might have done it. Yeah, Ren or Pony. Like, Pony is an excellent language if you want OOP with concurrency. Go play with Pony. Pony is cool. And its type system protects you from yourself. That's always a good thing to do. Okay, I need to write this out. So we want, let's do again an assert explicate control. I'm worried this is going to be big. So we need to define P2. And we're going to do this business again. Yeah, I think the ordering is going to be interesting. Maybe it needs to not be a list of diffs, but we'll find out. I think that because of the way that this is ordered, I think the order will be preserved because we've always done list map across them. So we're going to have a C definition for inc, and it's going to be x. It's probably x.1 integer t, and it's going to return an integer t, and then it's going to have C blocks, and of course it's going to be called inc, and then we'll have dict from list, and this will be inc is the block, right? And this will be I think this has to be a tail, so I think it's just return, which takes an expression, which is prim is an expression plus var variable x.1 int 1. Okay, that's not so bad. I wasn't gonna be worried. So what we want to show here, I think, we'll say this is tail call function. We need to do some stuff in, this is going to fail, by the way, in its current form. Let's put main in there. Okay, so this is going to be main, and it's going to have tail call. So tail call needs to be one thing I'm wondering is if this gets pulled up. Like, does this get assigned to a temporary variable? Probably not, because it looks, yeah, let's find out. Okay, so tail call takes a fun ref of inc 1 and a list of arguments, which is integer 41. Yeah, see, this is not atomic, so I think that what's going to happen, and we'll find out, is we're going to have a sign here, and assign takes, actually we're going to have sequence assign temp.1 funref inc, and then the next thing is going to be variable temp.1. Yeah, because and this is fitting with what they were talking about earlier in the chapter, where the way that we call functions, aside from where did it go? Probably in here, is going to be by indirect pointers. So it's going to be like this, right? So this will be assigned to REX probably, using the LEAQ instruction, and then we'll jump to it. We'll put 41 into, what is it, RDX? I forget exactly, and then we'll jump to this. Okay, let's see if we're right. We are not right. Okay, so we actually have a problem in that I don't know what I'm doing. How did I do this wrong? Okay, so we have define. Oh, did we run into this before? Let's get a yeah, I need parens around this. Around the arguments. That's what's wrong. It's not a very helpful one. It's just like, okay. So we did not get the same thing. Main comes first. So let's put main first. It's kind of weird, but I guess that makes sense. The shrink phase will prepend it to the list is probably what happens. Okay, so hey, I could compile this in my head. Yeah, let's continue, Willie. That's great. Let's continue that discussion on Discord. I think that is a really fun thing to do, and I personally like learning those low-level bits of Beam. But even Eric Steinman's Beam book is not really complete in terms of what are the opcodes in the virtual machine, and so it's not enough to go and say, hey, I can do all this lowering process like we do in this compiler toward Beam, and then write the opcodes myself. The Erlang compiler is just, it's got so much more sophisticated stuff. So that's pretty good. I think that it might be useful. I want to write something more complicated. Like I want to do a call that's not in tail position. But I think that let's just list out the things that are interesting that we need to test. Okay, so a call in expression position. We needed a call in effect position. And we need a function reference. in predicate. Well, we can't really do that. We can't create the conditions under which, because it would fail type check, right? Where we have a fun ref in predicate position. So it's really, that panic is just an internal guard for us. We could do a fun ref in effect position. I think that's about it. Let's see. We're almost at time, and I would like to go long today, just to do more of this. But I really need to go see my folks this afternoon. So I think that I might leave this as to-dos. Yeah. Tood. That's funny. Okay, to-do. There we go. And then we can come back to that next week. Except there won't be a next week. It'll be in 2 weeks. I'm finally going on vacation next week. So we won't be having a stream on this. This is really good progress for today, though. Whenever we get to this code generation stuff, like where it's not just recursive processing of a tree while mostly keeping the same shape, and it's more like, you know, requiring continuation passing, that always gets me confused. So let's go ahead and make a commit for this. And why do I have C2 copy? That shouldn't be there. I don't have it anymore. What is it? What is it talking about? All right. Well, we're just gonna. Oh, okay. It needed to refresh that view. That's an interesting bug. Okay. So let's look at the diff here. So we made format argument public so that we could reuse it. I need to let's do one more thing before I call it, and that's we're gonna go in here. We have explicate control already, so we just need to re-enable it. Okay, explicate control. Except it's not a few passes later. We have all the passes up to this point. So let's get all this. And then our C program, we don't import that, do we? So let's do that at the top. Oops. Except this has got to be C fun. Okay, so what we need to do is just overwrite everything that was above. So I'm just gonna paste and import that, please. Okay. Uncover get. Oh, we need to do. Oh, we never added remove complex operands. And I wonder if that's because we didn't have. Did we do pretty printing for this? We did. Okay, well, let's add that too. Never hurts to have more phases. Remove complex operands. And then we'll put that remove complex operands. Excuse me. yada. Okay, now, yeah, the problem was we didn't have remove complex operands in here at all. So we're going to copy that. And we're going to do remove complex operands. And this is going to be mon. Okay. And let's see here. We have uncover get twice. This needs to be remove complex operands. Trying to keep this in the same order so that so we're consistent. Okay, and then we can run our little program. Gleam run -m cluster dev start. Okay, and Algal and Deuce, if you're still here, this is the money. Okay, so I'm going to choose, let's do remove complex operands, and let's grab one of our programs from in here that are in our tests. Like, surely we had one that's way down here with, yeah, this is from the book. So we're going to, so let's compile that. And here's what our output for that is. So, you know, kind of complicated program. Note that these are still definitions. Inc down here is pretty simple. You know, it just gets a unified variable name. And then, you know, we've got map, which takes a function and a vector and then applies that function to both elements of the vector. And it has to allocate a vector to return. And let's see. Okay, and then so there's all that stuff. Let's see what happens with explicate control. And what we'll find, yeah, we've got a problem. We're going to find some issues with our formatting. So let's fix that formatting real quick in CFun. And this, we need a line break after that. Let's paste that again and do our explicate control. Okay, there we go. So we can see that we've kind of formatted our functions here with this comment, main, no arguments, integer. And then, you know, map is f.1, integer is a function integer to integer, v.2 is a vector of integer, and we return a vector of integer. And we're getting the start block, so to speak, is called map. And the same here for main, and the same here for inc. So we get to see what the variable names are. But let's have a look at the rest of our stuff. So main, right? So we're checking this main block 2. Right, go to main block 1. Okay, so we allocate, and here's our call. And I probably didn't need to say call, but it's interesting to see this is an expression position, right? Because we're going to operate on it. And then we do vector ref on that. So we've allocated that. We set field 0 to whatever vector1 was. It's 0. We set field 1 to 41. And then we call. So note that temp1 was assigned to the function ref map2. Temp2 was assigned the function ref inc1. So we can see we're calling temp1 with temp2, so inc is function ref, and temp6, which is this vector that we allocated and filled. And then what we return is vector ref taking the first field, well, the second field, index 1. Okay, so let's look at map. So here we are passed a function. We call that function. It's already in a variable, right? We call that function with temp1 and temp2. So this is working out exactly as I would expect. We can use example from from our test that we just wrote. Of course, we have it in the AST, but let's look at it here. And here we've got tail call. So we just assign inc1 to a temporary variable. We tail call into temp1, which is just jump, and then finally we'll return. Yeah. So I think this puts us in a pretty good spot. It'll be interesting to see what else we can do here. So we already can witness call in expression position with that other example. We'll probably want to see call in effect position, so inside a begin. Yeah. All right, cool. I think this is a good place to stop. I'll make a commit real quick, and then we will call it. So let's stage that, and we'll say chapter 7.7, explicate control, and C fun. Yep. And then I'll push so you all can see the code that we wrote today. So 2 weeks, we'll probably write these tests, try to make them as straightforward as possible. And then we will start in on select instructions. So that's going to be turning this C-like program into x86 assembly, which is the fun part. Thank you for the well wishes, and we'll see you in 2 weeks.